Okay, well, I suppose I better start. I'm just slightly bemused by this blue bar. Hopefully it's not going to lead to any trouble. Yeah, so some of you might have seen me talk about this a week ago in Scotland. So the new thing I've got since then is jet lag, unfortunately, and not a lot else. So yeah, it's going to be a bit of a repetition for you guys, I'm afraid. This is a joint work with Fabrizio, who's a PhD student in our group. He's not my PhD student, but he works for me on this stuff. Okay, so we've seen lots of diagrams. I feel a bit naughty, actually. I don't think I've got a single string diagram or network in my entire talk, so yeah, I'm maybe feeling a bit guilty about that. But the idea is to look for settings of these things. So just as a bit of motivation, we work a lot with these compact closed categories for these compositional things. So the sort of the canonical one possibly is finite dimensional Hilbert spaces for pure state quantum mechanics. And then we use the CPM construction to build a setting for mixed state quantum mechanics. There's an awful lot of literature on that type of thing. Similarly, and related to the work that Manoush spoke about, we can use real vector spaces to describe natural language semantics. And playing the same aim again, we can use the CPM construction to let us get incomplete information into play. Another compact closed category that's popularly used often as a counter model or as a toy model, but also as a setting for non-deterministic computation is REL, which is very familiar. We've just heard an awful lot about these cospans and correlations that do networks, the universe, and everything, so they're very powerful things. And spans crop up occasionally, although they're slightly less popular. So I've got this question down the bottom which says, where do we find new ones? I'm not sure that's quite the right question, because in a way you just asked Brendan, because he can do all of them. So the question maybe is how do we find the right one inside the space of things that Brendan is constructing? So that's what we're going to be looking at. Okay, so if we're going to look for new stuff, we need a sort of an unusual application area in which to start exploring. And one of the things that we've been looking at in our group is compositional models of cognition. And one of the sort of mathematical aspects that comes into play when in the literature about cognition is the importance of convexity. If it's not clear where that comes in, the simple-minded perspective is if you have a sort of space in your head describing your view of the world, this is a dog and this is a dog, then stuff in between better be a dog as well. It's as simple as that. So don't worry too much about where the convexity comes from. So you might then start thinking about, how are we going to get some notion of convexity involved in a compact closed setting. So initially we did this in a sort of ad hoc manner. We happened to know a construction that was going to get us in the right direction. We start with the finite distribution monad, which just sends a set to all the finite probability distributions on it. So that's a good thing for forming mixtures. We then do the usual Eilenberg-Moore construction on that. And the algebras in there are sets that take a finite mixture that we need to form a formal one and produces as a mixture. So it gives us a way of talking about convexity. And a standard fact is that these categories over Eilenberg-Moore categories over set are going to be regular, so we can form the category of relations on those things. And that's going to give us a compact closed category. And basically the way that the relations work is if you have a whole load of related bits, then you can form the same convex mixture of both, and you're going to get a related thing. So relations respect forming convex mixtures. Okay, so that sort of seemed to go well for us. We found an ad hoc trick that solved our problem, but then the literature about cognition also talks about metrics a lot. Here the motivation's much more straightforward. If you're near to something that you think about, then you should be similar in distance measures, sort of how far apart ideas are. But how are we going to get metrics into play? Yeah, well, our previous trick isn't going to pan out because the typical categories of metric spaces aren't regular, so we can't play that game again. So what are we going to do? So we're going to take a little bit of a detour in order to get to where we want to go. Binary relation on sets can obviously be thought of as a map from the product into the two-element set. And then there's a fairly obvious generalization that we've already seen in Manoush's talk, where we can generalize our truth values to live in an arbitrary quantile, and we can define identities and composition in these ways that basically parallel the way you'd usually compose relations, but substituting tensors for ands and the join for the usual or, so everything works in a fairly natural way. And we'll call these things Q relations for lack of a better name. And these guys form a category in a straightforward way. And if your quantile's commutative, then this category rel Q is a compact closed category. So we formed a compact closed category, but we haven't quite figured out how to get metrics involved yet. Okay, so we can put an order structure on the relations in this category in a completely straightforward way. We just order things pointwise using the quantile order. And in fact, this makes our category into a poset enriched category. So once we've got a category of that type, effectively it's a two category now, then we can talk about internal monads, which we seem to be going further and further away from this metric thing. We're going to converge in the next slide on the solution. So an internal monad is actually quite a simple thing in this setting. It just means that the identity is contained in your endo relation, and iterating your endo relation lives inside it. So reflexivity and transitivity condition is the way to read these things. And this parallels the usual definition of a monad in terms of a unit and a multiplication. I seem to have missed the name off here. But actually it's simpler because the axioms that need to hold haven't got any force here because everything's thin. So the reason we took this detour is we look at the internal monads in various different of these rel Q categories for different quantiles, we get some interesting things. So in the case where it's just true false, then an internal monad is going to be something satisfying these axioms, which basically means that it's a pre-order. So we've got a nice structured object in some sense. And if we change our quantile to just be the real interval from 0 to 1, and we have a look in here, this one's maybe takes a little bit more seeing, but basically it's a sort of fuzzy pre-order. It generalizes the notion of pre-order we saw before. So more interestingly, if we take a quantile where we take the extended positive reals, we reverse the order so that our join is going to be infimum, and we put additive structure on it. So this idea goes back a very long way. Then we get generalized metric spaces. So if we look at what the relatedness means, it means everything is zero distance from itself, and the transitivity condition becomes an instance of the triangle law, which is quite a nice little thing. And a little tweak on the choice of quantile actually gives us the ultrametric spaces instead. So that's sort of quite nice that we can get our hands on these things. Okay, so a little summary of what we've done. Basically, we've just done some ad hoc stuff in a way. Somebody in our group knows the construction, we use it and we see if we can get anywhere. So that sort of worked out nicely for these two examples. So we used this regular category construction, particularly for algebraic things. That's what we're going to pursue when we generalize in a minute. And then we use generalizing of truth values in order to get the metrics in play. And then we make a quick observation that actually these compact closed categories are hypergraph categories, so we're in Brendan's territory. And the questions that follow up then are, well, can we relate these two schemes? Can we do both at the same time? What have they got to do with each other? Can we vary relations in other ways? Relations are quite familiar things, so it might be easy to think about how we might extend the notion of relation. And then what happens if we vary the parameters on these things? So if we vary our quantile, are we going to get functors between things and whatever? Okay. Hysteresis. So the obvious place to start in generalizing things is to start with these simple ones with a different truth value object. They're fairly simple to deal with. And then think about how we're going to get the algebraic structure in play. So we saw an axiom of this form earlier, which basically said, if we've got related bits, then performing an algebraic operation on the bits leads to related composites. So respecting the compositionality of the situation, if you want to say that. We can't really say this here because now our truth values aren't living in a lattice, they're living in a quantile. So we just follow our nose, basically. We replace the ands with products in the quantile, and we replace this implication with the order structure inside the quantile. And we take this as our axiom to say that something respects the algebraic structure, so we're going to call these Q relations algebraic. So this seems to be a sort of fairly natural direction to go in. Okay, and the way we've written down our definitions, actually we can interpret all of this business in an arbitrary topos. So we've got sort of third direction of variations. We've got two so far. We had the choice of truth values and the choice of algebraic structure, and actually we can choose the sort of background mathematics that we're working in as well, and everything will work out fine. So the first theorem we have is if we have an arbitrary topos, an internal commutative quantile, and an algebraic variety in there, then we get a category of these algebraic Q relations. And this category has symmetric monoidal structure given by products. And it's also poset enriched via a sort of obvious generalization of the ordering that we saw before. And in fact, it's an instance of Brendan's hypergraph category. So this is kind of the spirit of what we're looking for is a parameterized procedure for generating new compact closed categories, where the parameters are preferably reasonably intuitive in terms of how you understand them. Okay, so we mentioned spans earlier. We're going to have a look at spans again now. So span's a simple thing. It just has a apex, then a couple of feet and a couple of morphisms. That's all the data involved. And one of the ways that you can think about these things, nice email, is that we have a constructive relation. So if we think of these things as sets, then we can think of the apex as proof witnesses, and we use this informal notation. We say that little x living in the apex relates A to B if it gets projected down onto A and B in the feet. Okay, so we've now got another relation-y thing, so we should be able to get this into the settings of relations that we've been dealing with so far. Okay, so, well, we kind of follow the drill that we followed before. We want to get a way of varying the truth values that are in play. And the obvious thing to do here is to add a sort of characteristic morphism to these proof witnesses that measures how strongly they're witnessing that things are related. And we'll call such a thing a Q-span. And we're going to write this type of notation here, saying something is related from A to V via this proof witness, and the strength of the relation is Q. So that's at least got us as far as generalizing the truth values. Okay, so again, we follow our nose and the drill that we had before. And we want to add some algebraic structure into play as well. So we basically do the same thing we did before. We require, if we have related bits via proof values with appropriate strength, then there should be a proof witness with strength Q relating the composites such that this Q is at least as strong as you get by gluing together all the truth values on the parts. He's busy, isn't he? Okay, so we note at this point that we also need order structure on these truth values in order to be able to write this axiom down. So we're in the setting of needing a partially ordered monoid or something along those lines at this point. Okay, so we get a second theorem now that if we have a topos and we have a variety within it, and we have Q, an internal partially ordered commutative monoid, then the algebraic Q spans form a category as before. This category is a hypergraph category, so again, we're living in Brendan's world. And in this case, it's pre-order enriched. I can't show that it's poset enriched. It seems to be pre-order enriched with an ordering as follows. So if we have two spans, this is the data for the spans, then we kind of expect to be able to find the weaker one within the stronger one, if we want to put it that way, such that the way that we map things in is a span morphism for the people that know what that means. And the truth values are stronger when we find truth values in the sort of stronger relation. Okay, so I don't know if I like the title of this slide, but I went with it anyway. We want to be able to relate this span construction to the rel construction. So the obvious thing to do is if our monoid that was pre-ordered comes from a quantile, then we can take all the different witnesses saying that things are related and then pick the best truth value. So we can kind of think of the need for a quantile in terms of the relation construction as acting as a sort of optimizer, picking the best way in which things are related. So that's the role that it serves. And it turns out that works out nicely as well. So if we pick a topos as usual and an algebraic variety, and an internal commutative monoid in our topos, then we get a strict identity and surjective on objects pre-ordered functor, squashing our witnesses down basically in order to find the best one in our category of relations, so we can relate these guys together.
So what does it mean to be identity and surjective on objects?
So you basically, because they are the same objects, it's actually going to send it to the same object, and it means it hits everything as well. So basically, possibly because the other category could be larger, but it's just a way of saying it. Yeah, it's not very precise. Yeah. Okay, so just to summarize what I've been quickly racing through, the aim at least is to provide a conceptually motivated procedure for searching around inside Brendan's large world of hypergraph categories and finding ones with properties that you might like. And we've ended up with 4 axes of variation via which that we can pick these things. We first have to fix an ambient mathematical universe, so a topos in which we're working. Once we've done that, we can pick an internal quantile that describes how truth should work. We can pick an algebraic structure, so that's the analog of this convexity that we saw earlier. And then we can choose between proof relevance versus provability in terms of whether we end up with the span or the rel construction. And I think Samson would shoot me if I didn't have examples at some point, so Samson can put the gun away now, I hope. We generate lots of the things that we see in the literature, so we see good old rel. We see this category rel that we wanted earlier that had the generalized metric spaces in it, also the one for the ultrametric spaces. With an appropriate choice of algebraic structure, we also get the category of convex relations from the other earlier example. And up to restricting to the finite dimensional stuff, we generate the category of linear relations that's interesting to various people here. And we also find various directions in which we might want to go probing for interesting models. For instance, this idea of can we combine the convexity and metric stuff together? Clearly, we're able to do that now. We might want to think about models in which the meaning of the either cognitive or linguistic stuff that we're dealing with or whatever the application is varying with context or with user or with time, that type of thing. And we can also exploit the presence of these proof witnesses in the span constructions in order to track not only what holds, but why it holds effectively, which would provide us with some new opportunities that we haven't had before. Okay, and then this mega conclusion basically describes everything I haven't been able to fit into the previous 19 slides. So it turns out that the constructions that we have are functorial in the choice of truth value. So if you have an appropriate homomorphism, then you get a functor between these categories. And I don't know what the correct word is. They're farcically nice functors. So, given Pavel's question earlier about how precisely I was describing these things, they basically preserve everything in sight. So they preserve everything on the nose as well. Everything's very nice. There's also the question of functoriality with respect to the algebraic structure. That seems an obvious thing to ask. And it turns out that's a more interesting question because our truth values are quantiles, so linearity starts to come into play. If you're interpreting one algebraic structure within another, then depending on the derived terms that you're using, you may need to copy variables or actually drop variables, and then questions of linearity come into play. But there is a functoriality theorem, or effectively 4 there, depending on which choices of the amount of structure you have on your quantile you choose. Or alternatively, you can restrict the relations that you're interested in, depending on how you want to see the situation. And in each case, with all of these constructions, we get a graph functor. So by that, what I mean is if you start with a function, you can take its graph to form a relation. And there's an analog of that construction for the constructions that I've described. And again, that thing's sort of farcically nice. It takes the finite product structure onto the monoidal structure in the categories that we're discussing. And it commutes with everything else as well. So taking graphs followed by the various functors we described commutes with each other. Looking further ahead, it's obviously an interesting thing to ask what the additional structure is within these categories of relations. When do we have zero objects, byproducts, and that type of thing? We'd like to look at functoriality in the choice of topos, but that's a slightly more complicated question because as you change the topos, you're kind of compelled to move the truth values around because they live within the topos, so that needs a little bit more thought. As Brendan mentioned earlier, this category of spans really should be a symmetric monoidal bicategory that is hypergraph in some appropriate sense. Now that sounds loads of fun, and there's enough fun, it's sort of a motivation for me to go and look, but a concrete reason for being interested in that is a well-known observation, I believe going back to at least Lack, that in the category of spans, if you look at the internal monads that we've been interested in the category of spans of sets, then those are exactly the small categories, so they're objects of interest. So we would like to be in this bicategorical setting to get at Lack's observation there. And we've been varying our truth values over quantiles. You can actually go further and have your truth values valued in a monoidal category. It's worth thinking about what exactly that might mean. But basically, that points in a direction where we could unify these span and rel constructions, because depending on whether your monoidal category is thin or whether it's a genuine category, will connect with this idea of whether you've got provability or proofs in the construction. And also, a sort of small conjecture here is if this monoidal category is symmetric, that will be the case in which you get a hypergraph category. But I don't know whether that's true yet. It seems an obvious thing to check. And that is everything. Thank you.
Question?
Go ahead. No, go ahead.
I'm the chair.
I was going to make a comment in the absence of immediate question. So my student, Kenny Courser, has a paper on getting...
Come out here if you're talking to the front. Can you stand up?
My student, Kenny Courser, has a paper where he gets symmetric monoidal bicategories of decorated cospans starting from Brendan's type of data. And so he used Mike Schulman's methodology of getting...
The double categorizing stuff.
To get the symmetric monoidal bicategory. So you should be able to...
Yeah, I'm aware of that as of about an hour and 15 minutes ago when I talked to Brendan. But yeah, I'm going to find out more. Yeah. I also have to apologize to you because I'm not as compulsively honest. All of my spans were obviously equivalence classes of spans, so I think I got away with it.
I have a question. So you're talking about cognition and garden fours and this stuff. Any particular model like that? I mean, people argue about it, right? They say, "Oh, convexity isn't an appropriate model." This sort of approach lets you be much more general quite easily.
Yeah.
So do you think that gives away? I mean, does the mathematics let you instantly grab some sort of maximally general model for, I don't know, cognition or something, such that no one could possibly object to it because it's so...
I'm not sure if we can have an objection-proof model, but the thing that we've managed, at least so far, is the convexity-based one was an interesting model from their point of view. So far we're after sort of teaser trailers for the good stuff, and Gudden Fors, who I can't pronounce it correctly, so I avoided it in the talk. He was certainly interested in what we were doing and is interested in collaborating further. So yeah, kind of being parametric and being able to balloon things up is an advantage going forward. But the way they describe things, I would say, is sort of pre-mathematical. So part of our function actually is to make more precise what they mean by convexity or what they mean by distance and various other notions that they discuss, because they're mathematical but up to a point, I would say.
I'm just going to, you had this thing about linearity in so is this the point that if the equations of your algebraic theory are linear, then everything is fine, otherwise you have to impose more structure on
Yeah, so if the derived terms that you're using when you're say you're interpreting a binary operation as some derived term in the second algebra, then you may be copying or deleting things when you build that derived term. And that axiom that I had that says if you have all of the related parts holding, then at least as true the combined thing should hold. That holds for the things in the signature without that's what we require. If you want that to hold on all of the derived terms, then you're going to need either more structure on your quantile, or you're going to need to axiomatize that your relations respect that a priori. So yeah, it's linearity in these derived terms, how they're using the variables.
Okay, well, thank you.